General Artificial Intelligence, AGI, aims to replicate the cognitive abilities of humans, enabling machines to perform any intellectual task a human can. Theoretical foundations of AGI include symbolic reasoning, neural networks, and evolutionary algorithms, each contributing to the machine's ability to learn, adapt, and reason. Key technical aspects involve integrating vast data sources, developing autonomous learning paradigms, and creating flexible architectures that mimic the human brain's complexity. The fundamental technical requirements for AGI include the ability to generalize knowledge across domains, acquire new information autonomously, and reason and plan effectively. AGI must possess robust learning algorithms that can adapt to unforeseen scenarios and dynamic environments. Additionally, it requires advanced computational power and efficient data processing to handle the complexity of human-like cognition. Mechanisms enabling an AGI to generalize knowledge across different domains include transfer learning, hierarchical representation, and the formation of abstract concepts. These mechanisms allow AGI to apply learned information from one context to another, enhancing its problem-solving capabilities. By building a multi-layered understanding of information, AGI can navigate diverse challenges with human-like adaptability. Current AI models often fail to transfer learning beyond narrow tasks due to their reliance on task-specific data and rigid architectures. These models lack the ability to abstract knowledge and apply it to unrelated domains, a key limitation in achieving true AGI. Overcoming this requires developing more flexible learning frameworks that can generalize across varied contexts and adapt to new challenges. An AGI can build a flexible, hierarchical representation of knowledge by organizing information into multi-level structures that reflect real-world complexities. This approach allows AGI to understand relationships between concepts and adapt its knowledge to new situations. By mimicking the human brain's ability to categorize and prioritize information, AGI can achieve a deeper understanding of its environment. To recognize and apply abstract concepts, AGI can utilize conceptual blending, a process where disparate ideas are combined to form new, innovative solutions. This approach mimics human creativity by allowing AGI to synthesize information from different domains, leading to novel insights and applications. By leveraging pattern recognition and contextual understanding, AGI can effectively navigate complex scenarios and adapt its reasoning to diverse challenges. AGI can autonomously acquire, store, and refine knowledge through reinforcement learning, where it learns by trial and error and feedback loops. This method allows AGI to continuously update its knowledge base, ensuring it remains relevant and accurate over time. By integrating neural networks and data-driven algorithms, AGI can efficiently process vast amounts of information, enabling it to make informed decisions and adapt to new environments. Architectures enabling long-term memory in AGI include recurrent neural networks, RNNs, and transformer models, which can retain information over extended periods. These systems allow AGI to recall past experiences and apply them to current situations, enhancing its ability to learn from history. By maintaining a dynamic memory structure, AGI can continuously adapt to changing environments and improve its performance over time. AGI can decide what information is valuable through attention mechanisms, which prioritize data based on relevance and context. By employing information theory principles, AGI can quantify the importance of data, ensuring that only pertinent information is retained. This selective process allows AGI to optimize its learning and focus on critical insights, enhancing its ability to make strategic decisions. Self-organizing knowledge structures like semantic graphs play a crucial role in AGI by mapping relationships between concepts and facilitating understanding. These graphs enable AGI to visualize connections and infer meaning from complex datasets, much like a human brain. By organizing information into interconnected nodes, AGI can efficiently retrieve and apply knowledge, leading to more coherent reasoning and problem-solving capabilities. To enable reasoning and planning, AGI must integrate logical frameworks and heuristic methods that allow it to simulate potential scenarios and make informed decisions. By employing constraint satisfaction problems and decision trees, AGI can evaluate multiple pathways and choose the most optimal course of action. This requires a sophisticated understanding of both short-term and long-term consequences, ensuring that decisions are strategically sound. AGI can evaluate complex, uncertain situations by leveraging advanced algorithms that simulate potential outcomes based on historical data and current variables. Techniques like Monte Carlo simulations allow AGI to predict probabilities and assess the likelihood of various scenarios unfolding. By continuously updating its predictive models, AGI can adapt to dynamic environments and make accurate forecasts. Probabilistic models, such as Bayesian networks, play a crucial role in AGI's reasoning by allowing it to infer causality and update beliefs based on new evidence. These models enable AGI to calculate probabilities and make decisions under uncertainty, much like a human would. By integrating causal reasoning, AGI can understand the interdependencies between variables and predict the impact of actions. Balancing exploration and exploitation is achieved through multi-armed bandit algorithms, which help AGI decide when to try new strategies and when to utilize known solutions. This balance is crucial for maximizing rewards while minimizing risks, ensuring that AGI remains adaptive and efficient. By employing epsilon-greedy strategies, AGI can dynamically adjust its approach based on real-time feedback and environmental changes. Promising learning paradigms for AGI include self-supervised learning, which allows it to generate labels from unlabeled data, and reinforcement learning, where it learns through rewards and penalties. Additionally, evolutionary algorithms mimic natural selection, enabling AGI to evolve solutions over generations. These paradigms provide AGI with the ability to learn autonomously, adapt to complex tasks, and optimize performance over time. Self-supervised learning empowers AGI by enabling it to generate insights from unlabeled data, reducing the need for human intervention. This approach allows AGI to identify patterns and learn autonomously, mimicking the way humans learn from natural experiences. By leveraging massive datasets, AGI can refine its understanding and enhance its cognitive abilities without explicit supervision. Reducing reliance on human-labeled data is crucial for AGI as it allows for scalability and efficiency in learning processes. Human labeling is often time-consuming and expensive, limiting the speed and breadth of data processing. By minimizing this dependency, AGI can accelerate its learning curve and adapt more rapidly to new information and environments. Large-scale pattern discovery enables AGI to engage in open-ended learning by identifying complex relationships within data. This capability allows AGI to generalize knowledge across different domains, enhancing its problem-solving skills. By continuously uncovering new patterns, AGI can expand its understanding and innovate solutions to unforeseen challenges. Techniques such as clustering algorithms and dimensionality reduction help AGI identify structure in raw, unstructured data. These methods allow AGI to organize information into meaningful categories, facilitating efficient data processing. By discerning underlying structures, AGI can extract valuable insights and make informed decisions based on complex datasets. Reinforcement learning enables AGI to thrive in open-ended environments by using trial and error to optimize its actions. Through reward models, AGI learns to maximize positive outcomes while avoiding negative consequences, much like a human learning from experience. This dynamic approach allows AGI to adapt to changing conditions and continuously improve its performance in unpredictable scenarios. To support general intelligence, reward models must evolve to incorporate multidimensional feedback that reflects complex, real-world scenarios. This involves designing systems that can balance short-term rewards with long-term goals, ensuring that AGI can make decisions that are both strategically sound and ethically aligned. By integrating contextual understanding and adaptive learning, these models can guide AGI in navigating dynamic environments with human-like foresight. Strategies to help AGI avoid overfitting to narrow goals include implementing diverse training environments and multi-objective optimization. By exposing AGI to a wide range of scenarios and encouraging it to pursue varied objectives, it can develop a more robust understanding of its tasks. Techniques like dropout, regularization, and cross-validation further ensure that AGI maintains flexibility and generalization capabilities across different contexts. An AGI can autonomously set and adapt its own learning objectives by employing meta-learning techniques that allow it to self-assess and redefine goals based on performance feedback. This involves creating a framework where AGI can evaluate its progress and adjust its strategies to optimize learning outcomes. By leveraging adaptive algorithms and self-improvement loops, AGI can continuously refine its objectives to align with evolving challenges and opportunities. Evolutionary algorithms and meta-learning can significantly contribute to AGI by enabling it to simulate natural selection and optimize learning processes over time. These methods allow AGI to experiment with different strategies, retaining successful ones while discarding less effective approaches. By fostering innovation through variation, AGI can develop novel solutions and adapt to complex environments with increasing efficiency. AGI architectures can evolve dynamically by utilizing modular design principles and self-modifying code that allow for real-time adaptation. This approach enables AGI to reconfigure its structure in response to new information or challenges, much like a living organism adapting to its environment. By incorporating flexible neural networks and recursive optimization, AGI can maintain optimal performance and scalability without being constrained by predefined limitations. Neural architecture search and self-improving models play a pivotal role in AGI by enabling the dynamic evolution of neural networks, allowing them to adapt and optimize over time. These models can autonomously refine their structures through trial and error, much like a sculptor chiseling away to reveal a masterpiece. By continuously enhancing their architectures, they can achieve higher efficiency and greater accuracy in processing complex tasks. Recursive optimization allows an AGI to continuously refine its learning algorithms, akin to a self-taught musician perfecting their craft. By iteratively analyzing its performance and making adjustments, AGI can enhance its problem-solving capabilities and adapt to new challenges. This process mirrors the way humans learn from experience, ensuring that AGI remains flexible and efficient in dynamic environments. AGI can integrate different data modalities to form a unified understanding of the world by employing cross-modal learning, which allows it to synthesize information from diverse sources. By combining data from visual, auditory, and textual inputs, AGI can create a comprehensive model of its environment, much like a detective piecing together clues. This holistic approach enables AGI to interpret complex scenarios and make informed decisions with human-like insight. To process and combine sensory inputs like vision, language, and audio, AGI utilizes advanced algorithms that mimic the human brain's ability to integrate information. By employing techniques such as multimodal fusion, AGI can seamlessly merge data streams to create a coherent understanding of its surroundings. This capability allows AGI to navigate complex environments and respond to stimuli with remarkable precision and adaptability. Architectures that allow for seamless fusion of multimodal data include transformer models and convolutional neural networks, which can process and integrate diverse inputs. These systems enable AGI to synthesize information from various modalities, creating a unified representation of its environment. By leveraging cross-attention mechanisms, AGI can prioritize relevant data and make cohesive decisions based on a comprehensive understanding. An AGI can build a world model by integrating diverse information sources, such as visual data, textual inputs, and auditory signals. By employing cross-modal learning, it can synthesize overlapping data to form a coherent understanding of its environment. This approach allows AGI to predict outcomes and adapt its behavior based on a comprehensive view of the world. One of the biggest perception challenges for AGI is dealing with ambiguous and noisy data from the real world, which can lead to misinterpretations. AGI must also contend with dynamic environments where contextual changes occur rapidly, requiring real-time processing and adaptation. Additionally, the ability to distinguish relevant information from irrelevant noise is crucial for effective decision-making. To understand and generate natural language in a generalizable way, AGI must develop contextual awareness and semantic comprehension beyond mere text prediction. By leveraging deep learning models and neural networks, AGI can capture nuances and intent in communication. This capability enables AGI to engage in meaningful dialogue and interpret complex linguistic structures with human-like proficiency. Current language models are limited in their ability to reason and generalize due to their reliance on pattern recognition rather than true understanding. These models often struggle with contextual nuances and abstract reasoning, which are essential for comprehensive language comprehension. Overcoming these limitations requires advancements in neural architectures that can simulate human-like cognitive processes. AGI can move beyond text prediction to achieve true semantic understanding by developing conceptual frameworks that mirror human cognition. This involves creating knowledge graphs that map relationships between concepts, allowing AGI to infer meaning and context. By integrating symbolic reasoning with neural networks, AGI can interpret language with a depth of understanding akin to human thought. Advanced approaches to grounding language in real-world concepts involve multimodal learning, where AI systems integrate visual, auditory, and textual data to form a cohesive understanding. Techniques like visual semantic embeddings allow AI to associate words with corresponding images, enhancing its ability to interpret and generate language with context. By leveraging cross-modal attention mechanisms, AI can achieve a deeper comprehension of language, akin to how humans relate words to their physical experiences. An AGI could develop causal reasoning and counterfactual thinking by employing Bayesian networks and causal graphs to model relationships between variables. These tools enable AGI to simulate potential outcomes and assess the impact of hypothetical changes, much like a scientist conducting experiments. By continuously updating its causal models with new data, AGI can refine its understanding of cause and effect, leading to more accurate predictions and informed decisions. Causality is essential for intelligence because it allows AI to understand the underlying mechanisms of events, enabling it to predict future occurrences and make informed decisions. Implementing causality in AI involves using causal inference algorithms that can discern cause and effect relationships from data, much like a detective solving a mystery. By integrating these algorithms, AI can move beyond mere correlation, achieving a deeper level of reasoning that mirrors human cognitive processes. Techniques enabling an AGI to simulate alternative scenarios include Monte Carlo simulations and counterfactual reasoning, which allow it to explore what-if situations. These methods enable AGI to evaluate multiple possibilities and determine the most likely outcomes based on historical data and current variables. By employing scenario simulation, AGI can enhance its decision-making capabilities, ensuring it remains adaptive and resilient in dynamic environments. Causal inference and structural models contribute to decision-making by allowing AGI to identify causal relationships and predict the consequences of actions. These models use probabilistic reasoning to assess the likelihood of various outcomes, enabling AGI to make strategic choices under uncertainty. By integrating causal reasoning into its decision-making processes, AGI can achieve a more nuanced understanding of complex scenarios, leading to better informed decisions. Leading architectural approaches for building AGI include transformer models, neurosymbolic models, and self-modifying code, each offering unique pathways to achieving human-like intelligence. Transformer models excel in language processing and pattern recognition, while neurosymbolic models combine symbolic reasoning with neural networks for enhanced cognitive capabilities. Self-modifying code allows AGI to adapt its algorithms dynamically, ensuring continuous improvement and flexibility in learning. Transformer-based models can be extended toward AGI capabilities by integrating memory-augmented mechanisms and modular architectures to enhance contextual understanding. By incorporating long-term memory and adaptive learning frameworks, these models can overcome current limitations in reasoning and planning. Additionally, advancements in interpretability and explainability will enable transformers to self-assess and refine their decision-making processes. Current transformer architectures face limitations in reasoning and planning due to their inability to retain context over long sequences and lack of causal understanding. These models often struggle with complex problem solving and abstract reasoning, which are crucial for achieving AGI. Overcoming these challenges requires innovative approaches that integrate memory systems and causal inference to enhance cognitive depth. Memory-augmented or modular transformer variants can improve generalization by incorporating dynamic memory systems that allow for contextual recall and adaptive learning. These models can store and retrieve information efficiently, enabling them to apply past experiences to new situations. By leveraging modular design, transformers can reconfigure their structures to better handle diverse tasks in complex environments. The next steps in making transformers more interpretable and adaptive involve developing transparent algorithms that provide insight into decision-making processes. Techniques such as attention visualization and explainable AI will help users understand how transformers prioritize information and make informed decisions. By enhancing interpretability, transformers can become more trustworthy and effective in real-world applications. Neurosymbolic models are considered a promising approach to AGI by combining symbolic reasoning with neural networks to enhance cognitive flexibility. These models aim to integrate the logical precision of symbolic systems with the adaptive learning capabilities of neural networks, creating a hybrid architecture that can tackle complex tasks. By leveraging both rule-based logic and data-driven learning, neurosymbolic models can potentially overcome the limitations of purely symbolic or neural approaches, paving the way for more robust AGI systems. Symbolic reasoning can be combined with deep learning to enhance abstraction by using neural symbolic integration, where neural networks learn to represent and manipulate symbolic structures. This approach allows for the automatic extraction of abstract concepts from data, enabling machines to perform higher-level reasoning. By bridging the gap between symbolic logic and statistical learning, this integration can lead to more sophisticated AI systems capable of generalizing knowledge across domains. Architectures that allow for dynamic switching between logic-based and statistical inference include hybrid systems that incorporate rule-based engines and probabilistic models. These systems can adaptively choose the most appropriate method for a given task, enhancing their ability to reason under uncertainty. By employing context-aware mechanisms, these architectures can seamlessly transition between deterministic logic and probabilistic reasoning, ensuring flexibility and accuracy in decision-making. Hybrid models can overcome the brittleness of purely symbolic or purely neural approaches by integrating robust symbolic frameworks with flexible neural networks. This combination allows for error correction and contextual adaptation, reducing the risk of failure in unpredictable environments. By leveraging the strengths of both paradigms, hybrid models can achieve greater resilience and versatility, making them well-suited for complex problem-solving in AGI. Self-modifying and self-rewriting code architectures can lead to AGI by enabling systems to dynamically adapt their algorithms and optimize performance over time. These architectures allow for continuous improvement through recursive self-assessment, much like a self-taught artist refining their technique. By incorporating evolutionary principles and adaptive learning, self-modifying code can facilitate the development of autonomous systems capable of self-directed growth and innovation. An AGI can enhance its learning algorithms by employing recursive self-improvement, allowing it to analyze its performance and modify its code for better efficiency. This process involves iterative refinement, where the AGI identifies inefficiencies and optimizes its algorithms to improve learning outcomes. By continuously updating its strategies, AGI can adapt to new challenges and maintain optimal performance over time. Developing AI systems capable of rewriting their own code presents challenges such as ensuring code stability and preventing unintended consequences. These systems must be designed to self-assess and validate changes to avoid introducing errors or security vulnerabilities. Additionally, maintaining a balance between autonomy and control is crucial to ensure that the AI remains aligned with human values and ethical standards. Evolutionary techniques can aid in designing adaptable AGI frameworks by simulating natural selection, allowing AGI to experiment with different strategies and retain successful adaptations. These techniques involve genetic algorithms that mimic biological evolution, enabling AGI to optimize its architecture over generations. By fostering innovation through variation, evolutionary methods can lead to robust and flexible AGI systems capable of adapting to complex environments. The current state of AGI is marked by significant advancements in machine learning and neural networks. Yet true AGI remains elusive. Breakthroughs needed include integrating diverse cognitive abilities and achieving human-like reasoning and adaptability. Experts suggest that cross-disciplinary collaboration and innovative approaches are essential to bridge the gap between narrow AI and general intelligence. The biggest missing pieces preventing AGI from becoming a reality include insufficient computational power and the need for advanced algorithms capable of generalizing knowledge. Technical challenges such as scalability and data integration also pose significant hurdles. Incremental advances in neuroscience-inspired architectures and cross-modal learning are crucial to overcoming these barriers and achieving true AGI. The quest for AGI is often hindered by the sheer computational power required to simulate human-like intelligence, with estimates suggesting it could take exaflops of processing power to achieve this feat. Current algorithms, while advanced, may not be sufficient, prompting researchers to explore quantum computing as a potential solution. A fundamentally new approach might involve biologically inspired computing, which mimics the efficiency of a human brain in processing vast amounts of information. Before AGI can emerge, it must overcome technical challenges such as scalability, where systems need to handle exponential data growth without losing efficiency. Another hurdle is achieving contextual understanding, enabling AGI to interpret and respond to dynamic environments with human-like adaptability. Additionally, developing robust safety protocols is crucial to ensure AGI operates within ethical boundaries and aligns with human values. Incremental advances in AI research, such as improved neural network architectures and enhanced learning algorithms, are gradually bringing us closer to AGI. By focusing on transfer learning, researchers enable AI systems to apply knowledge across different domains, enhancing their versatility. These small yet significant steps contribute to a cumulative understanding that could eventually lead to the development of a fully functional AGI. Experimental AGI systems like OpenAI's GPT-3 and DeepMind's AlphaGo showcase the potential of advanced neural networks in achieving human-like intelligence. These systems demonstrate the ability to learn complex tasks and adapt to new challenges, offering insights into the future of AGI development. By analyzing their successes and limitations, researchers can refine their approaches and accelerate progress toward true AGI. Research projects such as Google's DeepMind and IBM's Watson are pioneering AGI-relevant architectures by integrating deep learning with symbolic reasoning. These projects aim to create systems capable of generalizing knowledge and adapting to diverse tasks, much like a human brain. By exploring neurosymbolic models and self-improving algorithms, these initiatives are paving the way for the next generation of intelligent machines. Existing AI models like OpenAI's GPT-3 and DeepMind's AlphaZero exhibit early signs of generalization by mastering tasks beyond their initial training. These systems demonstrate the ability to adapt strategies and learn from experience, showcasing potential pathways toward AGI. By analyzing their successes and limitations, researchers can refine approaches to enhance cognitive flexibility and domain transfer. Lessons from AI systems that have failed in AGI-like tasks highlight the importance of robust learning frameworks and adaptive algorithms. Failures often stem from overfitting to narrow data sets and inflexible architectures, which limit the ability to generalize knowledge. By addressing these issues, researchers can develop more resilient systems capable of navigating complex environments and unforeseen challenges.